welcome back. A quick announcement. As you know, we will have the conference dinner tonight at Corrientes. 348. I mean, there's a number after. I think that 348 Marina da Gloria. And there will be 2 vans leaving from here at 5:05. We have a total of 35 places. I'm sorry, I try to make up more, but so it's for the invited speakers. Of course, Carsten, Christian, and I reserve, and then the first one who arrive. I'm sorry. But Uber is cheap. And we have a 3 hours package that goes between 18:30 to 21:30. And meaning that there will be the dinner, there is free bar with caipirinhas and beers for those 3 hours. Hopefully we will see the sunset. But at 9:30, there is also non-alcoholic drinks, Carsten. But at 9:30, they will stop giving us drinks and food. So it's important that we arrive there on time. Just for who will be unlucky to have to take the Uber, I give this information. Okay, and let me give the micro to the chair. That will give then the micro.
All right, welcome back to the afternoon session. Are you ready?
Yes, absolutely.
Right. We have Raluca Tanase, who will be speaking on partial hyperbolicity in the Hénon family.
Thank you for the introduction. It's a pleasure to be here in IMPA on such a joyous occasion. Carsten Petersen has always supported young researchers through his series of workshops and PhD lectures in Holbeck and Roskilde. They've now become a trademark, actually. And I've also had the opportunity to know him when we were office neighbors in Stony Brook during his 1-semester research visit there. So I'm happy to come here in person from cold Europe to sunny Rio to wish him happy birthday. So happy birthday, Carsten. I'll be speaking about complex Hénon maps, and every time I talk about 2-dimensional dynamics to an audience which specializes in 1-dimensional dynamics, I feel the need to give some justification on why we study Hénon maps. And the truth is that everybody has a different reason for studying Hénon maps, starting with Hénon, who introduced the Hénon family as a simplified model of another simplified model of a physical phenomenon known as atmospheric convection. But he soon discovered that even with so many simplifications, the map was so complicated that it had a lot of chaotical features that set it apart from the dynamics of 1-dimensional polynomial maps. Friedland and Milner, they've established the Hénon family as the family to study in the complex setting due to this nice theorem which says that every polynomial automorphism of C2 can be conjugate by another polynomial automorphism to one of the following maps: affine maps in the first category, elementary maps in the second category, which sort of have decoupled dynamics because the second coordinate is just a function of y. And the third one, which is from our perspective the most interesting, is the one with non-trivial dynamics, and it consists of compositions of Hénon maps. So there are these maps of the form x maps to p of x minus ay on the first coordinate and x on the second coordinate. This quantity a over here is the constant Jacobian of the map. So when a is different from 0, we are dealing with an invertible object. And in some sense, there is a similarity between this one. It's like the easiest way to go to 2 dimensions from 1 dimension, because when A is 0, essentially we have the polynomial dynamics over here. However, there are major differences because the polynomial dynamics is not invertible, the Hénon dynamics is invertible, and of course the differences do not stop here. Also in the complex setting, Hénon maps were used to produce examples of Fatou-Bieberbach domains, like these domains in C2, which are biolomorphic to C2, but they are not the entire complex plane. And these Fatou-Bieberbach domains, they can have various boundary properties. So Bieberbach studied Hénon maps because these Hénon maps, if they have sinks, for instance, or semi-parabolic fixed points, then the basin of attraction is a Fatou-Bieberbach domain. Okay. Now, there is also some universal aspect to the Hénon family, and more precisely, if we look in the Hénon-like family, so if we take quadratic Hénon maps and add a certain perturbation, then these ones, they're general enough that they appear in other families of maps as well. More precisely, they appear in unfoldings of homoclinic tangencies between the stable and unstable manifold of a saddle periodic point in dissipative systems with one unstable Lyapunov exponent. So you have such a configuration over here. You see a tangency developing, and you can perturb it within a 1-parameter family, say, so that to destroy the tangency, and then the map nearby, it behaves like a Hénon-like map. So this is what we would like to advertise as the universal presence of Hénon maps in higher dimensional dynamics. Sorry? The G over here, it makes it a Hénon-like map. So we don't have nearby, when we do the unfolding, we don't necessarily have a Hénon map. We have a Hénon map plus some perturbative term.
Before you unfold, you just wanted to say the G is the unfolding.
Yes, we could, exactly. We could assign over here some parameters and make this one be the unfolding. But no, actually, no. Actually, I don't want to think of it that way just because I want to think it as a general phenomenon in general families. So I would like to think that whatever family I start with and which has the properties over here, which has a homoclinic tangency, I can add to it a certain perturbation, destroy the tangency, and then the nearby dynamics over here is governed by such a Hénon-like map. Okay, so if I start with this map, yes, this is going to be an unfolding of this map. But if I start with any other map with these properties, then I have a Hénon-like map over here. Okay, and I will focus on quadratic Hénon maps. So to me, the polynomial over here is going to be x squared plus c. A is going to stand for the Jacobian. And whenever you hear me talking about C and A, these is the parameters that I'm referring to. From the point of view of dynamics, we focus on 2 invariant sets. K plus and K minus are the points with bounded forward and respectively bounded orbit in C2. J plus and J minus are the topological boundaries of K plus and K minus. And J over here is the intersection of the two. J plus, J minus, and J are all called the Julia sets of the Hénon map, with the difference that J plus and J minus are unbounded and always connected, whereas J over here is bounded, and it may or may not be connected depending on the particular Hénon map that we choose. But they all share fractal behavior, so they all have common features in this sense. Tanya talked a little bit more about these objects in her talk on Monday, so I won't go into the details, but feel free to stop me if I've missed some definitions. In my talk today, I would like to focus on the Hénon maps which have some nice geometric properties. And partial hyperbolicity over here is a relaxation of the notion of hyperbolicity that we all know. And it means that we have two invariant families of cones, call them vertical and horizontal for simplicity, but they need not be so straight. In the vertical cone, we have strong contraction. The contraction factor over here is strictly less than 1. In the horizontal cones, we don't know exactly what we have. We may have contraction, expansion, we may have some neutral behavior, but whatever it is, it's tame. It's dominated by the strong contraction in the other families of cones. Now, when we deal with dissipative Hénon maps, the strong contraction over here is superfluous. It just follows from the fact that the Jacobian is less than 1. So we could alternately use the notion of partial hyperbolicity and that of dominated splitting. Now, in the complex setting, Ljubic and Peters, and in the real setting, Pujals and Sambarino, have shown that a moderately dissipative Hénon map, moderately dissipative, meaning in this context that the Jacobian is less than a quarter, if it admits a dominated splitting on the Julia set J, then it has only finitely many periodic Φ2 components, each being either an attracting or a parabolic basin. Φ2 components, they just mean components of the connected components of the interior of K plus, together with the escaping component, the one which escapes to infinity under forward iterations. Now, these Hénon maps with dominated splitting, they're morally just 2D counterparts of 1D polynomial maps which do not have critical points in the Julia set. Knowing that the number of attracting or parabolic basins is finite doesn't really mean that these maps are trivial or that they are well understood in general. And actually, the number of such objects is finite, but it's not bounded in any way by the degree of the map. It's by now, I think, a classical phenomenon, the Newhouse phenomenon, which tells us that there are Hénon maps with infinitely many sinks. Of course, these maps are not partially hyperbolic, but there is a whole way from one sink, let's say, to infinitely many sinks. There is a whole entire thing that can happen going from small Jacobian to other Jacobians. Now, going in a slightly different direction, Milner has studied these compositions of two quadratic maps, x squared plus a, x squared plus b, and he defined the swallow-shaped parameter space. This is all in the real, so these maps are real polynomials, and this is a real parameter space. A, B is in R2 with the property that 0 does not escape under forward iterations of QB composed with QA, or 0 does not escape under forward iterations of QA composed with QB. And the parameter space is such a swallow-shaped parameter, and Berger later proved that this space embeds in the parameter space of Hénon-like maps, and he used it to construct real Hénon maps with sufficiently small Jacobian and exactly two sinks. Now, these examples over here of real Hénon maps, they lie towards the tip of the Mandelbrot set at c equals -2. So it's a region which we understand a little less even in the one-dimensional situation, because it's full of these satellite copies of Mandelbrot sets. Okay, now going from 2 to infinity, there are many intermediate phenomena that one may have in the Hénon family. For example, Benedict and Parmesano, they've shown that for every k greater than 1, there exists a set of parameters for which the corresponding Hénon map has at least k attractive periodic orbits and some additional stuff, like a strange attractor. However, the techniques used in this construction, they do not allow any fine properties, any control on the fine properties of the Julia sets. So in particular, we cannot say that this is a map with k sinks, which is, for instance, partially hyperbolic, or it's not partially hyperbolic on its corresponding Julia set. And the construction over here, again, it's a real construction. So it concerns the Hénon maps with real parameters. OK, so if we aim to find Hénon maps which are partially hyperbolic, but they're not hyperbolic, a good way to start is by looking at one-parameter families of complex Hénon maps, which correspond to these curves of parameters in which we have the Hénon map has an n cycle with a fixed eigenvalue, which is a root of unity. So what is a semi-parabolic fixed point? It's what's a semi-parabolic cycle? It's a fixed point of some iterate of the Hénon map for which the Jacobian of the iterate has two eigenvalues, lambda and mu. One is strictly less than 1 in absolute value. The other one is a root of unity. And what we could do is we could fix lambda, a root of unity, and let the other eigenvalue vary. And this kind of condition, this kind of constraint on the eigenvalue, it's going to define an algebraic curve in the parameter space of complex Hénon maps, corresponding to the Hénon maps which have an n cycle with a prescribed eigenvalue lambda. So this is what I will think of as per n lambda. And whenever I talk about fixed points, it's more convenient to just call them p lambda. So one of the first results on Older theorem is that there exists delta, so that if we look in one of these per n lambdas at the small perturbations, we call them, so we look at the Hénon maps with Jacobian less than delta, then these maps are going to be partially hyperbolic on the Julia set J. Necessarily, they are not hyperbolic because they have a semi-parabolic fixed point in the boundary. And we can say we know almost everything about them. So some of the features that are listed over here, they form a structurally stable family on J and J+. By structural stability, we don't mean structural stability in C2, because the map is not hyperbolic, but we mean structural stability within the curve per n lambda. They have connected Julia sets, which are equal to J star, the closure of the saddle periodic points. It's not known in general whether J is equal to J star, but it's true for such families. The Julia set J is homeomorphic, the Julia set is homeomorphic to the quotient of a solenoid by an equivalence relation, and they arise naturally. They don't flow out of nowhere. They arise naturally, and they sit in the boundary of hyperbolic components of the Hénon kinetic dust locus. I'm going to show you a picture with what I mean. And the Julia set J+ in a bidisk, and I'm really thinking of the Hubbard filtration picture of C2, but it could be a bidisk which contains the Julia set J, is really fibered over the Julia set of the polynomial. So this is like JP cross D. And much like we think of the Julia set of the polynomial as a quotient of S1 by a lamination, this is the same way in which we view the quotient over here. It's like an S1 cross D, quotiented by a lamination, but the identifications, in some sense, they're the identifications defining the strong stable manifold of the semi-parabolic fixed point. In one dimension, if you talk about the fat basilica, it's the external rays landing at the parabolic fixed point that do the identifications. Here in 2 dimensions, it's some identifications which look exactly the same, and the resulting object of the identification is the strong stable manifold of the semi-parabolic periodic point. So we would like to kind of use this one as a starting point to dive into the parameter space of Hénon maps with larger Jacobian, not just with small Jacobian. OK, but before doing that, let me show you just a quick picture over here. So on the right, you look in it's a complex picture. It's a complex parameter picture. Both of them they represent a tentative drawing of the connectivity locus for the Julia set of a one-parameter family of Hénon maps. In here, this one corresponds to P minus 1. So the common feature of the Hénon maps in this picture is that they have a fixed point with one eigenvalue minus 1. And over here in the picture, on the picture in the left, they represent Hénon maps which have a 3-cycle with one eigenvalue 1. And the regions which we know how to describe, they're these regions over here. These connected components which contain 0, which contain the polynomial with a parabolic fixed point in the interior. Okay, now a theorem of Dujardin says that the Hénon connectedness locus is closed. And we know in this one-parameter family that what we have over here in the interior is Hénon maps with closed Julia sets. So this boundary over here, whatever it is, it's going to consist of Hénon maps with connected Julia sets. And that...
So the parameter here is the Jacobian A.
Yes, the parameter in here is the Jacobian A. We fix lambda, root of unity. On the picture on the right, lambda is minus 1. And we look at P minus 1. So it's the set of complex Hénon maps which have one fixed point with one eigenvalue minus 1. The free parameter is the other eigenvalue, but it's the same as the Jacobian in this case. And in here, we do the same, but for a cycle. And these pictures are not really quite easy to obtain. They're a little easy around 0, but they're a little more complicated afterwards because there are many critical points to take into account. It's a paradox with the Hénon family. On one side, it has no critical points because it's an automorphism. On the other side, it has plenty of critical points, so it's hard to know which one is relevant for the features one studies. Okay. Let me just quickly tell you a little bit about the fact that these semi-parabolic Hénon maps, they are naturally in the boundary of hyperbolicity because over here we have, if we perturb a little bit these parameters, so if we look at nearby one complex families of Hénon maps, one parameter families of Hénon maps, by putting in here lambda, the parabolic eigenvalue times 1 plus t, where t we think of as a real small parameter, then what we can show is that these families, they contain hyperbolic Hénon maps with connected Julia sets. So in one dimension, it's like we go from the parabolic parameter, which connects to bulbs of the Mandelbrot set, into one of the two bulbs. This is like the analog over here in several dimensions. And if we go in the right direction, then we are going to produce hyperbolic Hénon maps, which are topologically conjugate on their Julia sets to the semi-parabolic Hénon map on its corresponding Julia set. Now, later on, Bedford and Dujardin, they've shown that if you have two Hénon maps, and if these two Hénon maps are conjugate, not just on the Julia set, but on an open neighborhood of the Julia set, wherever this conjugacy makes sense, then hyperbolicity is actually an invariant of such conjugacy. So if one map is hyperbolic, then it forces the other map to also be hyperbolic. We usually think of hyperbolicity as a geometric property of the derivatives, but they can see it at the conjugacy level, the topological conjugacy level, as soon as the conjugacy is not just on J, but on a neighborhood of J. So in some sense, this theorem over here is strong because it's a conjugacy which cannot be extended to a neighborhood. It's just on the Julia set J. Because this semi-parabolic Hénon map is not hyperbolic, so it would violate the other theorem. Okay. Now, talking about these semi-parabolic parameters, Dujardin and Lubitsch have shown that a moderately dissipative Hénon map with a semi-parabolic cycle can be approximated by Hénon maps with homoclinic tangencies. And this is realized by perturbing the semi-parabolic cycle so that there is a bifurcation happening. So there is an egg beater over there which creates some sort of dynamics which goes to infinity, but in such a way that it can create some recurrences and some quasi-recurrences. And from there, one can perturb further to create maps with homoclinic tangencies. Now, sort of using the same kind of passing through the egg beater in a controlled fashion, we are able to show the following thing. So not only do these semi-parabolic parameters sit in the boundary of homoclinic tangencies, but they also sit in the boundary of hyperbolicity, for which we know that the Julia set is a horseshoe. This is a theorem for small parameters, so it's not for moderately dissipative. It's for our regions which come from small perturbations of polynomials over here. And the way in which we view the perturbation is by putting an index over here, which is 1 plus it. I'm going to explain you on the picture, perhaps, how it goes. So if you are at the cusp of the Mandelbrot set, you have a one-parameter family over here, P1, which consists of complex Hénon maps, which have one fixed point with one eigenvalue 1. Now, at the cusp over here, P1 plus T and P1 minus T, they point the same way. They go towards the interior over here. Because at the parabolic implosion, you have two fixed points, and they will have multipliers like 1 plus T and 1 minus T. When you go over here, it's like you take P1 plus IT, because the parabolic fixed point, it splits into two fixed points which do not sit on the real line. They sit symmetric with respect to the real line, but in the complex. Oops. OK. And this is a set in which we understand the semi-parabolic Hénon maps. Perturbing towards the left gives us regions of hyperbolicity with connected Julia sets, which have the same topological model as the Julia set of the partially hyperbolic map. We also have continuity of Julia sets and everything in the Hausdorff topology. Coming from the right, we have a different phenomenon. It's a parabolic implosion phenomenon due to Bedford, Smiley, and Vedada. Sorry. Huh. No. Too much. Too little. This is going in some other direction. Let's see. I've seen it happening to other people when they presented, and I said, it's not going to happen to me because I know how to push the buttons. Apparently, not so much. Yes. I said, no, I'm not going to show you the presentation when in the middle of the talk. And I'm not going to wish happy birthday to Carsten every time I want to move to the next slide, you know? Yes. OK, so going to the right over here, there is this semi-parabolic implosion phenomenon of Bedford, Smiley, and Vedada, which says that JJ plus, KMP, K plus, they vary discontinuously with the parameters as t goes to 0. And this is where we have the horseshoes. So this semi-parabolic thing is approximated by horseshoes. OK, but knowing that this is true, it makes us wonder what other things may implode over there. So we have the critical locus that Tanya talked about on Monday. And this critical locus is one of the notions of critical points that one may formulate for the Hénon map. This is the set of tangencies between the foliations of the escaping set U plus and the foliation of the backward escaping set U minus. It's always a closed, non-empty analytic subvariety of U plus enter U minus. we actually understand it as a model in very, very few situations. We understand it for the HOV region, which lies further away from these perturbations. But in the perturbative setting, we understand it for perturbations of Hénon maps with connected Julia sets, which are hyperbolic on their Julia sets. This is Lubitsch-Robertson theorem, which says that the critical locus is disconnected, and it consists of one primary component, which is like a disk, and it's forward and backward iterations. This is something that also holds for these perturbations with semi-parabolic fixed points. And we also have the description of the critical locus, which is due to Firsova, corresponding to Hénon maps, which are hyperbolic on their Julia sets, and they have disconnected Julia sets. And in that case, the model is more complicated because it consists of accountable collections of spheres with two counter sets removed, and which are connected between themselves by a finite but still growing number of handles. And the question is, how does the critical locus vary with respect to the parameters once we make this passage? So once we pass from this region here to this region here, from this to this. And one thing that we want to show is that this description, the complicated description, the one with spheres and with handles, it actually holds throughout the region going into the parabola P1, and then it implodes. So basically, these spheres with handles, at some point, all the handles, they disappear all at once. And from the spheres, what remains is the disks, the ones which map to each other under forward iterations of the map, which correspond to the model for Hénon maps with connected Julia sets towards the left. So not only do we have implosion in the Julia set, but we also have some sort of implosion in the critical locus, which defines the Hénon map. OK, so I've told you a little bit about what happens for small Jacobian from the point of view of partially hyperbolic Hénon maps that we understand better. But there is a fundamental question remaining. How do we find partially hyperbolic Hénon maps in the big parameter space of complex Hénon maps, which are not singular perturbations of polynomials? One thing is finding them, and the other thing is proving that they indeed have the features that we are looking for. So, for example, Hubbard looked at the following Hénon map, x squared minus 0.38y minus 1.05 nx, a map with very specific parameters. It's a map which has an attractive cycle of period 3 and an attractive fixed point. And he conjectured that the map over here is hyperbolic. Hénon, when initially starting to investigate these families, also had some specific numerical parameters for which certain features like these were true. So the question is, how could one prove that examples like these are hyperbolic, or in what sense they are generic? How can such examples be found other just by doing random computer experiments? Other programs for testing hyperbolicity for certain specific Hénon maps have also, with real parameters, and it's important, have also been developed by Zinarai and Yutaka Ishii. But again, it's about testing for a specific thing in some specific places. OK, so one approach that one could think of is using these semi-parabolic curves over here, trying to intersect them, and then at the intersection parameter, look at the properties of the Hénon map. If they intersect in the dissipative setting, because not all semi-parabolic curves want to intersect in the dissipative part. Some, they just intersect for conservative Hénon maps or for some other Jacobians which we do not control. But some of them, they do intersect nicely, and when they do intersect nicely, they create some Hénon maps which have two semi-parabolic cycles. And these would be our candidates for showing that the map is partially hyperbolic, has some partial hyperbolic structure on the Julia set. And obviously, they would not be singular perturbations of quadratic polynomials, because quadratic polynomials do not have two attracting dynamics, two parabolic fixed points. And then one could make the transition, much like what I've described in the one-dimensional situation. We could perturb from here to here in the parameter, in the complex parameter space in C2, to turn these parabolic cycles into attractive cycles in the right way, so that maybe perhaps the parabolic dynamics is topologically conjugate to the hyperbolic dynamics on the Julia set. A specific candidate that one has in mind is to take a look at these things. So we have pair 3, 1, which correspond to Hénon maps, which have a 3 cycle with one eigenvalue 1, intersected with pair -1 n, which correspond to Hénon maps, 2 to the n, sorry, which correspond to Hénon maps which have a cycle of period 2 to the n with one eigenvalue -1. And these maps, these parabolic curves over here, they really want to intersect. Okay. So because we are in low degree, one can explicitly do the computations for pair 3 lambda, end up with a degree 6 polynomial in C and A, but which is actually only degree 3 in C. And actually for lambda equals 1, there is a more appealing formula over here, which is C is a quadratic function of A. It's the same as for fixed points, actually. So it's kind of easy to just draw it and see over here how they intersect. In the A plane, so we are going in the full parameter space of the complex Hénon maps. A equals 0 defines the regular Mandelbrot set picture. We have these curves. So P minus 1 intersects the Mandelbrot set at the polynomial, which has a parabolic fixed point with one eigenvalue -1. And then there is the period doubling by bifurcation over here, leading to the other curves, P2 to the n -1. And there are these corresponding semi-parabolic curves in C2, which intersect the Mandelbrot set at these points, leading up to a curve which sits over the Feigenbaum polynomial over here. Now, on the other side, we have this satellite copy of the Mandelbrot set, and this one, the polynomial over here at the cusp of the satellite copy, is the one which has a cycle, a 3 periodic cycle with one eigenvalue 1. So if we look at pair 3, 1, this is the parabola whose algebraic equation I've drawn on the other side, and it looks like this. And if we go over pair 3 lambda and we do the same plot, they are all going to intersect these curves over here. And we can actually plot what they intersected into, and you can see that it's like a cardioid picture in all of these vertical-like curves. Okay, so we've got these intersections, and now what I would like to focus on is the little parallelogram over here. So we've got a first intersection between pair 1, 3 and P minus 1. It gives me a Hénon map with 2 semi-parabolic fixed points, which I can conveniently perturb over here, so that, maybe I can look in a zoom, so that we create a hyperbolic, well, candidate for a hyperbolic Hénon map with 2 attractive basins. And that would be over here. Okay. Now, Hubbard's parameter over here is something like this one, up. So it's not exactly a perturbation of our setup because it has very concrete numerical parameters. So I cannot say that for epsilon and t, which are small enough, we exactly land on this parameter over here. And moreover, it's sort of going in the other direction. So it's not going to be towards those maps which have the same model on the Julia set as the one over here. So this is going to us in the right direction. This is going a little bit in the wrong direction. But right and wrong over here, you see, two are very complicated things to define. OK. So let's take as an example this intersection between pair 1, 3 and p minus 1. We've got a very concrete Hénon map over here with two parabolic cycles, one of period 1 and one of period 3. The Jacobian is 2 minus square root 3, so it's 0.27. It's a little bit over 1/4, which makes it hard to use any theorems, any general theorems about structures of semi-parabolic maps, which end at 1/4. So this one is just slightly above, so that it makes life more difficult over here. And now the work in progress is to show that this map is actually partially hyperbolic on the Julia set, and moreover, it has connected Julia sets. So not only is it partially hyperbolic, but we understand a little bit more about it, about its connectivity properties. This is a real picture because these parameters, these parabolic curves that I've shown you, they intersect in the real. So this is a real picture over here of the dynamics of the Hénon map with one cycle with a 3 periodic with eigenvalue 1, and the other one with a semi-parabolic fixed point with eigenvalue -1. The dots are so small over here that I can't even see them, and I know where they're supposed to be. So the 3 periodic orbit is here, here, and somewhere here. And colored in red, yellow, and green, you have the semi-parabolic attracting basins of this 3 cycle. And somewhere over here is the semi-parabolic fixed point with one eigenvalue -1. So in blue and in gray, you see the two Bieberbach domains, well, in C2. In here, you see the two basins of attraction of the semi-parabolic fixed point. So blue and gray, everything in the blue and gray region over here, it all converges to this fixed point here. And it's a slightly off choice of color because I think this is better on the next picture. Because in here, what I've done is to perturb from the semi-parabolic fixed point into a direction in which we push the semi-parabolic fixed points as sinks. So we perturb the neutral eigenvalue. The semi-parabolic fixed point over here, which was here, it develops into a 2 attractive periodic cycle, which you see here and here. And then these are the basins of attraction. And the same happens for the cycle, which was former semi-parabolic. Now it's an attractive cycle over here. OK. But overall, you see that the Julia shape, the shape of the Julia set has not changed. So all the changes happened in the interior of K-plus. So let me go back over here a little bit to the curve P-1, where we see this phenomenon happening. At a equals 0, you have the parabolic polynomial with one eigenvalue -1. Near a equals 0, in P-1, we have the region of small perturbations of Hénon maps which are partially hyperbolic but not hyperbolic, and for which we understand almost everything about how they behave. Now, nearby, and by nearby I mean all the way to the top, is the map which has two semi-parabolic basins. So landing over here is the map that I've told you about, which lies at the intersection of pair 3, 1 with P minus 1. And going from here to here, there is a chain of bifurcations that you can perhaps see better here. So in the picture on the right represents a zoom around the top parameter. The one with two parabolic fixed points sits here. And this is the chain of components, a chain of components going to here. Okay. Now, one feature of this picture is that the bifurcations which lead from here to here, they happen on the real line of parameters. This is a complex one-parameter family, but actually the bifurcations, they happen on the real line. And I'm going to tell you why that is. But first, let me go over some brief key points of, yes? These are not conjectural, no, it's better. It's like an approximation of the connectivity locus of the Hénon map within some one-parameter families of Hénon maps. So, for instance, over here, what we do is we take the Hénon map, which has two complex parameters, A and C, but we don't regard it as A and C. We regard it as lambda mu, where lambda mu are the two eigenvalues at one of the fixed points. We fix lambda to be minus 1. We let mu vary. Mu is essentially the Jacobian. So if I pick a parameter somewhere over here, it's like I'm picking mu. So I form the map H lambda mu. It's like I know exactly what the parameters C and A are for the Hénon map. You cannot. It's a very, very rough approximation, which is, well, over here we know it's true. Like over here next to A equals 0, we know it's true. And for the rest, it's a very rough approximation of what the connectivity region of the Julia set might be based on some critical points which escape or don't escape. And don't make me define critical points for you at this stage. So, so over here is A equals 0, and here is 2 minus square root 3. So it's 0.27, roughly.
You said that was where it intersects which?
It intersects, so let me go back just a little bit. It's going up this curve here, from here to here. So it intersects pair 3, 1. It's going from here to here.
Did you ever try to draw these pictures much larger?
But they become very imprecise. That's the point about, for the Hénon maps, it's a very tricky business about drawing in the parameter space. And if you know what phenomena to expect, you know how to carefully choose your critical points so that they produce sort of the pictures that you want. If you give me some random region of the Hénon map to explore, since I don't know what dynamical bifurcations happen over there, I do not know how many critical points would be relevant for the pictures that one has. So it's a very complicated thing, and it's by no means it should be taken as a precise bifurcation locus for the connectivity region. That's the last thing that I would like you to understand from here, that these are exact parameter pictures that one, it's just a rough approximation, okay? I use fractal stream, which is built upon, it's, I do have an algorithm over there, but it's like Matt Newton, under the direction of John Hubbard, before my time in Cornell, was asked to produce an up-to-date version of a fractal stream. And it partially works if you have some insight on what things you should correct, and if moreover you know what dynamics to expect. So it's worse than running a program with no manual. You know, you have to have the manual and and some other insight. Yes. Okay. Good. So let me just go over quickly over here. These are some rough key points that one follows when trying to prove partial hyperbolicity. Partial hyperbolicity is actually easier to prove near the semi-parabolic fixed points because we have an entire machinery over there which we have developed for small perturbations, but locally around the semi-parabolic fixed points they sit the same way. You can design families of vertical and horizontal invariant cones, and in which in one direction it's strong contraction, in the other one it's weak expansion, in which the expanding factor goes to 1, but precisely as you converge to the strong stable manifold of the semi-parabolic fixed point. And these ones need to be matched outside of the neighborhood of the semi-parabolic fixed points with some other families of cones in order to create a partially hyperbolic metric in the neighborhood of the Julia set J. Let me skip a little bit over here. And then there is a sequence of tangencies going from small Jacobian into these Hénon maps with two parabolic basins. And these ones, they can be understood, they can be explained as a sequence of heteroclinic tangencies between the strong stable manifold of the persistent semi-parabolic fixed point and the unstable manifold of some distinguished, actually of the other fixed point. The Hénon map has two fixed points. They don't bifurcate in this family. One of them stays semi-parabolic with eigenvalue 1, eigenvalue minus 1. The other one, it stays hyperbolic. So it's between these two things that one creates and develops tangencies. Now, let me go back over here on the picture for just a little bit. For small perturbations for which we understand the model in J plus over here was the Julia set of the parabolic polynomial cross dr locally in a bidisk. It's not globally a fiber bundle, but in a bidisk which contains the Julia set. This is how it looks like. Is the Julia set is the fat basilica cross dr. Now, what do we see from the fat basilica in the real? We only see two fixed points and their orbits. So we only see the parabolic fixed point, the hyperbolic fixed point, and their orbits which lie on the real line. Now, this is sort of what happens over here. So we are going from here to a first bifurcation. But it's on the real line, the bifurcation. So it's a bifurcation that one could see in the real. In our model, what we see in the real is the semi-parabolic fixed point with its strong stable manifold. We see the hyperbolic fixed point. Well, maybe I could show you on a picture. So this is the strong stable manifold of the semi-parabolic fixed point. This is the hyperbolic fixed point, which has an unstable manifold and a strong stable manifold. And we see all the intersections that the unstable manifold and the stable manifold, they create. In the complex world, there is also an asymptotic curve of points which converges to the semi-parabolic fixed point under backward iterations, but you do not see it in the real, because in the real, everything between these two lines is part of the basin of attraction of the semi-parabolic fixed point. So all you see over here is attraction towards the semi-parabolic fixed point. And now there is a first heteroclinic tangency happening between this unstable manifold of the saddle fixed point and the strong stable manifold of the parabolic fixed point. And this is what corresponds in this picture to this parameter here. Now, this one, it sits in the boundary of the region of Hénon maps for which we have connected Julia set. So this one here is also going to have connected Julia set. Sorry. You had a question? Oh, sorry. What we want is to go up, and going up means that we can push this tangency in a way so that it does not disconnect the Julia set. And how we can do it is just by pushing it from one basin to the next. It's like pushing, yeah, it's now a tangency between the strong stable manifold here in the picture. It's a tangency here, but we can think it here on the strong stable, on the local strong stable manifold, and we can make it go from here to here. So within a one parameter family of real parameters, we can make this tangency pass from here to here. And our weakness to the connectivity of the Julia set is this unstable manifold here. And there is a theorem of Bedford and Smiley saying that if there are no critical points of some type, in U plus enter this unstable manifold, then the Julia set is connected. But this one is going to stay only in the stable manifold, which is in J plus, and it's going to pass from one basin to the next. I mean, there are two components. Locally, there are two components of this semi-parabolic basin. So we make it pass from here to here. And so it never escapes to infinity. It always remains bounded. OK. And then we go to a further secondary bifurcation in which there is still a tangency between the unstable manifold of this saddle fixed point and the strong stable manifold of the persistent semi-parabolic fixed point. There is a second tangency developing here, and there is a third tangency developing here. And the more tangencies, I mean, this is the first, the second, the third, and so on. And the more we go up this chain of tangencies, then we start seeing a recurrent phenomenon. Because what we have over here is something which goes here, 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 and then back up. Let me tell you that this is a combinatorics that the Hénon map really likes, because the Hénon map sends the y-axis to the x-axis, the x-axis to the parabola, and then the only thing that one needs to control for this kind of semi-recurrent behavior is to make the return of this region back up. So that's where the Jacobian greater than 0 and real sort of comes from. And the more points, so these ones, they behave like they would, you almost see the period 3 cycle emerging from these bifurcations, except that now we are somewhere along the tangency path. So after they do this kind of threefold dynamics, at some point, they end up on the strong stable manifold of the semi-parabolic fixed point. So they eventually converge to the semi-parabolic fixed point here. But going up and going up, they eventually create the 3 cycle. So in the pictures here, these are the tangencies that I've described, going up and going up. And every time we do this thing is we put the tangencies go from the stable manifold. We never let them escape to infinity. This kind of tangency, we move it in a way that it never escapes to infinity. So it does not disconnect the Julia set in itself.
Are you saying that there are no other bifurcation going on at the same time in this sequence?
Work in progress. Yes, this is roughly what I'm saying, but I don't claim it as a theorem at this point. OK, and these are some pictures from the unstable manifold in which the tangencies occur. It's the first three pictures, therefore the same parameter. You see over here something which looks like a very distorted basilica. Over here, everything over here is still converging to the same semi-parabolic fixed point. It's a zoom because the picture is self-similar. So you can see something which will eventually implode into creating the basin of the 3 cycle with an eigenvalue 1. Okay, I think I'm going to stop here because I think I went a little bit too much.